welcome back to today's video lecture. In the last video session, we have studied few things, and today we are going to continue. Uh, okay, okay. So we have studied in the last video lecture, that is about the vapor pressure of solutions of liquid in liquid, right? Solutions of liquid in liquid. That is, both your solute is liquid and solvent is also liquid. And based on this, we have studied the Raoult's law. Raoult's law. So in this video lecture, we are going to study vapor pressure of a solution of solid in liquid. Okay. So in this video lecture, we are going to study about vapor pressure of solid in liquid. Okay. So your solid is acting as a solute, and your liquid is going to be solvent. So what is special about here? Your solute which you have taken here is a non-volatile solute. Non-volatile solute, and your solvent, it is acting as a volatile solvent. Volatile solvent. So based on the interaction between the non-volatile solute and the solvent, which is volatile, we are going to study the second case of Raoult's law. Raoult's law. Okay. 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 So here what happens is, what is the effect of non-volatile solute towards volatile solvent? Basically what happens is, so when you dissolve a non-volatile solute into a solvent, some of the solute particles comes and occupies the position of solvent molecules. Okay, the solute molecules occupy the position of solvent molecules in the surface of the liquid. Okay, the surface of a solution. So when they occupy the position of solvent molecules, so they decrease the tendency, that is, they decrease the solute, that is, they decrease the escaping tendency of solvent molecules into the vapor phase. Into the vapor phase. So these solute molecules, when they occupy the position or the place of solvent molecules or the solution surface, so they decrease the escaping tendency of the solvent molecules into the vapor phase. Since the solute particles are non-volatile, they won't escape into the vapor phase. Only the solvent molecules are escaping into the vapor phase. So the tendency of this escaping nature is decreased by the solute particles, so due to which the vapor pressure of the solution decreases. Okay, so let us understand this with the picture which I have presented over here in the slide. Okay, so in the slide you can see over here we have two containers, And in the first container, I have taken a pure solvent. Basically, I have told you in the beginning only, your solvent is going to be volatile in nature. And this is covered with an inverted bell jar, okay, in order to capture the vapors. In the second case, I have taken the second beaker, which is having both solute and solvent. Your solute is non-volatile solute and solvent is volatile in nature. Okay. So in the first picture, you can see over here, we have taken a pure solvent which is volatile. Most of the molecules over the surface of the liquid, they have high tendency to escape into the vapor phase. So they escape freely into the vapor phase and they exerts vapor pressure. Okay. And they contribute vapor pressure. Okay. So now this is the case in the first diagram. Now when I add solute particles or solute into this pure solvent, so it becomes a solution. Since the solute particles are non-volatile in nature, so they block the escaping tendency of this solvent molecules, which are volatile in nature. So that you can see over here in the second diagram. So in the second diagram, it will clearly shows that less number of solvent molecules present in the vapor phase. Okay, so the escaping tendency has been decreased by the non-volatile solid. So this was studied, and according to Raoult's law, what we can say is the vapor pressure of the solution vapor pressure of the solution is directly proportional to the mole fraction of the solvent in the solution. So I'll consider the solute and I number it as 1. Okay. And the solvent, I take it as 2. Okay. And since the solute has no effect or no contribution towards the vapor pressure, only the solvent is having a considerable concentration contribution towards the vapor pressure. Okay. So what it does is, you can say P2 is equal to P naught 2 into X2. That is P2 is nothing but vapor pressure of solvent, nothing but P2. P naught 2 is nothing but vapor pressure of pure solvent, and yeah, X2 is nothing but mole fraction of solvent in the solution. Okay, so this is the second definition of Raoult's law. That is, vapor pressure of the solution is directly proportional to the mole fraction of the solvent in the solution, and this is the mathematical form of Raoult's law for non-volatile solute dissolved in a volatile solvent. Okay, so so by this we cover both the cases of Raoult's law. First is Raoult's law for non-volatile solute, sorry, volatile solute dissolved in a volatile solvent. The second case we have discussed about the non-volatile solute dissolved in a volatile solvent. Okay, so let us move further. Okay, so now we have this thing, that is Raoult's law as a special case of Henry's law. What is this? So as you know that according to Raoult's law, when we studied the Raoult's law for a liquid type of solution, liquid type of solution, we got that the two components exerts an individual partial pressure. Okay, that is PA, if I take the first component, is equal to P naught A into X, right? Similarly, the second component PB is equal to P naught B into XB. So this was the equation which we got from the two liquids, that is both are volatile in nature, and they exerts the individual partial pressure. We got this equation, right? So which is constant over here, that is the vapor pressure of the pure component is going to be constant. Okay, it will not change. So similarly for just now what we saw is, that is for the solid liquid type of solution, again the Raoult's law, what we got the equation is P2 is equal to P naught 2 into X2, right? Here also the pure solvent which is volatile in nature, the vapor pressure is going to be a constant, it will not change. Similarly, according to Henry's law, what we saw is the partial pressure PA is equal to KH constant into the mole fraction. So the PA is nothing but your partial vapor pressure, and KH is the Henry's law constant, and XA is the mole fraction of the solute which is present in the solution, which is in equilibrium with the gaseous phase. Okay, so here the constant is going to be KH, that is Henry's constant. Henry's law constant. So in both the cases, when we compare the Raoult's law and Henry's law, only the exceptional thing is, that is your constants are different, but remaining equation is going to be the same. That is PA. I'll take another ink. Okay, that is PA is equal to XA. Okay, this is going to remain same, only the constants are different in both the cases. So that's why comparing both the equations, we get that partial pressure of volatile components or the gas is directly proportional to the mole fraction, right? That we got from this equation. So hence Raoult's law is a special case of Henry's law, only the constants are different. Okay. Next we'll move further, that is we have ideal and non-ideal solution. So we have studied about the ideal gases and non-ideal gases, right, in first PUC. So in second year, we are going to study about ideal and non-ideal solutions in solution chapter. So what is this ideal and non-ideal solution? Okay, on the basis of Raoult's law, liquid type of solutions can be classified into ideal and non-ideal solutions. Okay, so first we will take up the ideal solution and understand what is an ideal solution. It is also important. Okay. So ideal solution. So how do you define an ideal solution? An ideal solution is that solution in which each component obeys Raoult's law under all conditions of temperature and concentration. So when you take a liquid type of solution, each component, if you have number of components, each component has to obey the Raoult's law under any kind of temperature and concentration. This is very important, the temperature and concentration. Then only such kind of solution we call it as ideal solutions. Okay. So these ideal solutions must have to obey certain conditions. The first condition is there will be no change in the volume on mixing the two components. Say for example, you have two components, component A and component B. When you mix these two components, there should not be any change in the volume. That is, delta V mixing should be equal to 0. If delta V mixing is equal to 0, then there will be no change in the volume. Similarly, the second condition is there will be no change in the enthalpy. That is, neither the heat is absorbed nor the heat is given out when you mix both the components. That is, delta H mixing also should be equal to 0. When they satisfy both these conditions, then only we can accept the particular solution is behaving as an ideal solution. Okay, this is the first thing. Let's take the real example and try to understand. Say for example, you have 50 cm cube of benzene, and also you have 50 cm cube of toluene, 50 cm cube of toluene. Okay, so when you mix both the components, that is benzene and toluene, so it becomes a mixture of benzene and toluene. So 50, it becomes totally 100 cm cube. Okay, when you mix both this solution, both these components, so you get a mixture of benzene and toluene, where you can see there is no change in the volume. Okay, no change in volume. You're going to get exactly 100 cm cube of total solution, and also there will not be any change in the enthalpy. No change in enthalpy has been observed. So that's why we consider the mixture of benzene and toluene as an ideal solution. Okay. Okay. I can pause the screen and we can go through it. Okay. So practically, when you see this ideal solution, practically there is no solution which is ideal. Okay, ideal solutions are not exist. So when do we consider this solution as ideal? Is only when the concentration of the solute is very less. The concentration of the solute is very less, then only we consider or the solution is exist as an ideal solution. Or sometimes if the solute and solvent have similar structure and same kind of polarity, then such kind of solution they behave almost like an ideal solution. Okay, so practically there is no such kind of solution which is exactly ideal, but they behave like an ideal solution only when the concentration of the solute is going to be very less, or the structure, that is structure of both the solute and solvent, is exactly similar and the polarity is similar, then only they behave as an ideal solution. Okay, let us see some of the examples of ideal and non-ideal solution. Examples. Okay. Example 1 is, just now I have given the example, that is benzene. plus toluene. Okay. Second one is N-hexene plus N-heptane. Okay. Third one, ethyl bromide and ethyl chloride. Okay. Fourth one, chlorobenzene and bromobenzene. So you can consider these examples as an ideal solutions example. And if it is asked in the exam, you can give the examples. Okay. Okay. Next, we will move further. Now let us come to non-ideal solution. Second type of liquid-liquid solution, that is non-ideal solution. So what is a non-ideal solution? So any solution that is non-ideal solution is a type of solution in which each component does not obey, okay, does not obeys Raoult's law over an entire range of concentration. Okay, such kind of solutions we call it as non-ideal solutions, right? So here also non-ideal solutions has to follow or satisfy certain conditions. The first condition is there will not there will be change in the volume on mixing the two components. When you mix the two components, the change in the volume will take place. That is, delta V mixing is not equal to 0. Similarly, the second condition is there will be change in the enthalpy when the two components are mixed. That is, delta H mixing is also not equal to 0. So they have to satisfy these two conditions, then only they behave as a non-ideal solution. Here, non-ideal solutions are further being classified into two different types. That is, the first one is non-ideal solution showing positive deviation from Raoult's law. From Raoult's law. Similarly, you have non-ideal solution showing negative deviation from Raoult's law. Okay. The examples we will discuss with the positive deviation and negative deviation. Okay. So this is about the non-ideal solution. Let us take the first case, that is non-ideal solution showing a positive deviation. Okay, from the Raoult's law. Raoult's law. So you can see the graph over here in the right side corner. I have the graph which is indicating, that is, in the y-axis I have taken the vapor pressure, x-axis is the mole fraction. Okay, so here the mole fraction is changing as we move from left side to the right side or from right side to the left side. So that is being plotted. Already we have seen the graph which is giving a straight line. When you plot vapor pressure against mole fraction, you're getting a straight line over here. But along with that, you have a blue colored line which is a curve shape. So it is having certain deviation from ideal solution. Okay, so what is the cause? What is the cause of deviation from Raoult's law? Okay, the green colored line is showing, it is indicating for the ideal solution. Okay, this is for the ideal solution, and the curved shaped green colored line is for the deviation from Raoult's law. Is the deviation from Raoult's law. So now let us understand what is the cause of deviation from Raoult's law. Okay, so the cause of deviation lies in the molecular level. Molecular level. Okay, basically it is about the interactions. Interactions between the molecules. Okay, so let us take an example, general example. I'll take a solute and a solvent. Okay, I'll consider solute as capital letter A, solvent as B. Okay, so generally when you take a solute, you have a solute-solute interaction, right? That is solute bond will be there. I'll write it as A and A. Similarly, you have solvent-solvent bonds, that I'll write it as B. Okay. Before mixing, they exist in this form. When you mix the solute and the solvent, the solute-solute bond will break and solvent-solvent bond also will break, and a new bond is formed. That is, solute is going to form a bond with solvent. That I will write it as A and B. A is forming a bond with B. So this new interaction is going to be very weak interaction. The new bond which is formed between the solute and the solvent is going to be a weak kind of interaction. Due to the weak interaction, they feel very easy to escape into the vapor phase. Into the vapor phase. Okay. So the solution which is being formed, the interaction is going to be very weak. So due to which most of the molecules will try to feel and escape into the vapor phase, and they contribute certain vapor pressure. So the vapor pressure will increase. Yeah, the vapor pressure will increase. That's why you're getting a graph which is showing a positive deviation from normal ideal solution. Okay. Let's take the regular example. An example of ethyl alcohol plus cyclohexane. Okay, so the mixture of ethyl alcohol and cyclohexane will show the positive deviation from Raoult's law. So generally when you take these ethyl alcohols, you have intermolecular hydrogen bonding is present. I'll write the structure C2H5 OH. Okay, C2H5 C2H5. Okay, so now ethyl alcohol, they in the pure form they have intermolecular hydrogen bonding. Okay, delta positive on hydrogen, delta negative oxygen, positive negative. Okay, so these intermolecular hydrogen bonding are very strong bonds. Okay, now In the pure form, ethyl alcohol does not have any kind of deviation from Raoult's law. But when you add this cyclohexane into the ethyl alcohol, this cyclohexane will come and occupy the space in between the ethyl alcohol linkage. So once they come and occupies the space in between the two ethyl alcohol molecules, they will decrease the interaction between the ethyl alcohol molecule. Okay, that is ethyl alcohol and cyclohexane. A new kind of interaction is formed. That is, ethyl alcohol is interacting with cyclohexane. So this new interaction is going to be a weak kind of interaction, due to which you can easily expect this molecule to come into the vapor phase and increase the vapor pressure. Okay, due to increase in the vapor pressure, there is a positive deviation from your normal ideal gas curve, ideal solution curve. Okay, so this is about the non-ideal solution showing a positive deviation from Raoult's law. Now let us uh, take some of the examples, few more examples. First example is acetone plus carbon disulfide. Acetone plus carbon disulfide. Okay. Second one is acetone plus ethyl alcohol. Third example, acetone, mixture of acetone and benzene. Fourth one, carbon tetrachloride and chloroform. Mixture of carbon tetrachloride and chloroform, and carbon tetrachloride plus benzene. Last one, carbon tetrachloride and toluene. So all these are examples for non-ideal solutions which are showing positive deviation from Raoult's law. Okay, and this is the graph which represents the positive deviation from the Raoult's law, and these are the examples for positive deviation, right? I hope you understood. Now let us move to the second type of non-ideal solution, that is, which is showing a negative deviation. Okay, showing a negative deviation from Raoult's law. So why there is a negative deviation? You can see over here in the graph, the curve has it is bent towards the lower side from the solid line. Okay, so why there is a decrease in the vapor pressure is basically the same way. The cause of the decrease in the vapor pressure is because of the molecular interaction. Okay, molecular interaction. The same way as I told you, if I take A as solute, okay, and B as solvent, the solute interaction solute interaction is going to be weak. It's a weak kind of interaction. Similarly, the solvent interaction is also a weak kind of interaction. Okay, So when you mix the solute and the solvent, the solute particles will form a new interaction with the solvent, and a new bond is formed. This interaction is a strong interaction. Since it is a strong interaction, you cannot expect these molecules to be present in the vapor phase very easily. So that's why that does not contribute much towards the vapor phase. So that's why in the graph you can see there is a lot of deviation from from the Raoult's law, which is a negative kind of deviation. That is, vapor pressure is decreasing. Vapor pressure is decreasing, decreases because of the strong interaction between the solute particles and the solvent molecules. The vapor pressure decreases, and there is no much contribution towards the vapor phase. That's why there is a negative interact, that is negative deviation from Raoult's law. The very general example, regular example, that is CHCl3 plus acetone is the best example for non-ideal solution, which is showing negative deviation from Raoult's law. So if I write the structure of this, you have Cl, Cl, and H. Okay, acetone, chloroform, and then acetone. Here we have an hydrogen bonding between chloroform and then acetone. Oxygen atom of acetone will form an hydrogen bonding with hydrogen atom of chloroform. Okay, so I have delta negative of the chlorine, delta positive over hydrogen. Okay, so this hydrogen bonding is going to be a very strong bond or strong interaction. Okay, so because of this strong interaction between the solute and the solvent, so due to which the escaping tendency of the molecules will decrease and less contribution towards the vapor phase. So that's why there is a lot of negative deviation takes place from the Raoult's law. Okay, I hope you understood from this example. Now let us see the certain more, like little more examples which actually gives negative deviation from Raoult's law. Okay, I've taken only one, I've given one example here. I'll give a few more examples. Okay, first example is chloroform plus benzene. Okay, second one, chloroform plus diethyl ether. Third example, acetone plus aniline. Fourth example, HCl and water. Fifth example, nitric acid and water. So I no need to explain every example. It's all the same way in the molecular interaction. So just consider all these examples behave as the same way how I showed you just now. Okay, So they all show the same kind of deviation, that is negative deviation from the Raoult's law. So these are the examples for negative deviation from Raoult's law. Okay. So today's class, what we have discussed is, that is, basically we have discussed about the vapor pressure of solid liquid solution in Raoult's law. Okay. And we have discussed about the special case of Raoult's law over Henry's law. And we have studied about the ideal and non-ideal solution. What are the conditions that they have to satisfy, and certain examples from ideal solution and certain examples from non-ideal solution. In case of non-ideal solution, we have seen two different deviation, that is, one is positive deviation, one is negative deviation. That is, in case of positive deviation, we have studied about what is the reason for the positive deviation and what is the main cause for the positive deviation and certain examples. Okay. Similarly, for negative deviation, what is the cause of the negative deviation and some of the examples for negative deviation. Okay. I hope you understood, and I'll see you in the next class. Thank you, students.